Thank you very much, Srinivas. Before I start, I'd like to thank MSC Software for giving me the opportunity to present this webinar. I trust that you will find it useful. All right, my topic for discussion today is going to be simulating mine blasts to improve vehicle safety. The contents of the presentation consists of 8 sections. In the first one, I'll just give you a brief background to ESTEC, who we are and what we do. Then I'll provide some motivation as to why we want to simulate mine blasts when we are designing military vehicles. In section 3, I'll look at how exactly simulation can aid the design process. And then in section 4, the exact approach that we use. I'll then illustrate how simulation aids the design process through a demonstration model, for which the results will be presented in section 6. I'll then highlight a number of new Dytran features that are very useful if you are interested in performing mine blast analysis. And then finally, I'll give you some recommendations to take note of if this is something that you want to pursue seriously in the future. Right. So just some background on ESTEC, the company that I work for. ESTEC is located in South Africa, right at the south of the continent. We have 3 offices in the country. The head office is in Pretoria, which is where I'm located. As you can see, I've indicated it there on the map. And then we've got 2 support offices, one down in Cape Town and the other on the east coast in Durban. ESTEC's philosophy when it comes to doing business basically revolves around providing clients with a complete solution. We don't believe that if you give clients a good piece of software, you've given him a solution. You need to provide him with the correct people and the best practices in order for that to make a difference in his business. And that's really what we strive to do on a daily basis. ESTEC has been a partner with MSC Software for over 20 years now. We are in a unique position in the South African market because we have been involved with defense companies in the area of mine blast simulations for approximately 14 years. The mine-protected vehicles industry in South Africa is rather lucrative and vibrant. It obviously goes through cycles with conflicts around the world, but in general, hardware that is developed in South Africa is sought after in the international market. So that obviously puts us in a position where we've got industry that requires our support and knowledge. And ESTEC is in a position where we've got a number of our technical personnel who have worked in the defense industry before becoming technical specialists at ESTEC, which puts us in a unique position when we support the industry. Right. So before I give you any information on actually performing mine blast simulations, I think it's first prudent to investigate why we would actually want to simulate and provide motivation in that regard. To answer that question simply, it's to produce better quality vehicles more cost effectively. So that's the simple answer. I'll go into a bit more detail and provide a breakdown to provide more concrete evidence of that. If we look just basically at requirements when you create a mine-protected vehicle, there's really 2 scenarios that you could follow. The one is you've got a vehicle that needs to meet specifications that are set out by your client. Routinely, if you are looking to provide a mine-protected vehicle to an international client, they will specify that that vehicle needs to meet a certain level of mine protection, which would be set out in a certain code. For instance, a STANAG 4569 is typically used to specify the type of test, mine blast test, that a vehicle needs to pass. Going through the certification process is often costly and time-consuming, and if in the process of trying to get certification you fail, that can really set you back significantly. So simulation can aid you in that regard to try and avoid failures. The other sort of scenario that you could look at is if you're building a vehicle that isn't for a specific client, you're just building a vehicle for sale to on a general market. Here you're wanting to gain a competitive advantage over the rest of the industry, and I think simulation can play a key role in that regard with regard to mine protection, but also all other aspects of a vehicle's performance, like ride and handling, noise and vibration, fatigue life. These are all areas that will see great improvements if simulation is implemented competently. Okay, so that was the brief answer, but the real reason that people want to simulate and would really come down to making money. So I've just sketched up a scenario here based on our experience in the industry. If you want to do a certification test on a vehicle, you typically have to hire a test range, which will cost you in the region of $38,000 in South Africa. Elsewhere in the world that will obviously vary, but I think this gives you a good ballpark value. To develop a vehicle prototype for testing will take between 2 to 3 months on average, which will give you a total cost of about $100,000. Just bear in mind that excludes material costs. So that's just looking at the labor cost involved in getting that prototype into a state where it can be tested. So it's not a cheap process to go about certifying a vehicle. What happens if you fail a certification test? Well, then your problems get compounded. You've got to hire the test range once again, another $38,000, and then you'll take approximately a month to repair and modify your vehicle. So you're looking at an additional cost of $60,000 in the case of a test failure. So from a money perspective, there's really a lot of motivation behind looking to perform simulation. If we now compare the costs that I've just spoken about in the previous slide to those of a simulation model, we can see immediately the advantages that exist. All right? So if we just look at the initial development cost of the prototype, a physical prototype will cost about 7 times more than a simulation model. The development time for a simulation model will be 4 times faster than that of a physical prototype. So on the initial development, both in terms of cost and time, you save significantly. And then this is really where things start to favor simulation heavily, is when you have to perform modifications on a vehicle in case of a test failure. If you have to perform those on a physical prototype, the implications are pretty severe. If those only have to take place on a simulation model, you're looking at the 30-to-1 ratio between the physical and the simulation model. So you can implement changes at the cost and time ratio of 30-to-1, which is very, very significant. Okay. So other than looking purely at the money, there are some real technical advantages to doing simulation, and those I've listed here. I'll just go through them very quickly. The simulation model, once you've set up one model, you can use it for a number of mine blasts. Okay, so typically you'd want to test the vehicle for a number of mine locations, and simulation model allows you to do that very easily, whereas a physical model, you basically get to shoot once and it's over. Then you've got to repair the prototype and get it ready for an additional test. So there's a huge cost saving that you get from using simulation over a physical model there. Then when it comes to analyzing and obtaining data from the simulation or the physical test, simulation has a a really significant advantage in that regard. First of all, the results are all clear, so there's no dust, smoke, and risk of overexposure or underexposure, which all come into play if you're doing physical tests. In addition, test equipment can easily malfunction under the harsh conditions of a mine blast test, so that's an additional risk that you take if you go the physical testing route. A number of times when you look at the physical model after a test has been performed, you'll have to postulate what caused specific behavior. So you're going to have to look at the post-mortem evidence and sort of try and piece things together, whereas in a simulation environment, you've got access to the results of the entire duration. You can establish exactly what happened during the event. The other very important point that I'd like to bring to your attention is the fact that if a vehicle fails a test in a virtual environment, this is generally not viewed in a negative light. Most of the time, if you're doing simulation, this is viewed as a part of the development process. Whereas if you go and actually test a physical prototype, a lot of the time a client will have a keen interest in that result, and it's very embarrassing if your prototype fails that test. So on that ground, a simulation model can save you a lot of embarrassment if it is used competently. All right. I need to mention a few caveats before I continue. I've painted a very rosy picture for simulation, but there are a number of things to keep in mind. Simulation will never replace testing. This is especially the case when you're performing mine blast analysis. The reasons for this are twofold. Basically, there's a lot of variability in the manufacturing and testing that cannot be adequately accounted for in the simulation model. And secondly, simulation models need to be verified and validated. There's just no escaping that fact. Simulation is not a certification tool, it's a design tool. That's the point that people that are new to mine blast simulation often get confused about. They think if you pass this, if in your simulation you pass, in the test you'll definitely pass. That's not the case. The aim of the simulation at the end of the day is to try and reduce the amount of physical testing, but not eliminate it. Right. Okay, so having given motivation for why simulation is a route you would want to follow during the design process of a mine-protected vehicle, let's now look at various aspects of a vehicle where simulation can be critical and a really significant aid during development. All right. So the first one is with regard to the hull shape and its integrity. Obviously, you need to ensure that there is no hull rupture when a blast impacts that hull. And in order to ensure that, you need to select both appropriate plate thicknesses and materials. When you choose a material, you often are faced with conflicting criteria, high strength versus ductility. You want a high strength steel, but often that comes at the cost of ductility. I mean, mine protection, ductility is your friend. Also to keep in mind is the fact that most of these vehicles will not only be mine protected, but also ballistic, offer a significant level of ballistic protection. And ballistic protection often requires high strength steel. So you're sort of playing off those two characteristics against one another when you choose a plate thickness, well, or rather a material for your hull. The second point is the positioning and design of joints. This is really a critical aspect when it comes to designing mine-protected vehicles. You need to make sure that any welded joints are positioned where the effect of the blast will be least significant. And if they are going to see a lot of the blast load, they should be protected appropriately. And then the other sort of form of connection that is used is bolted joints. These are very dangerous to use in mine blast protection scenarios simply because If a bolt fails, you're looking at a very high-speed projectile flying somewhere within that occupied compartment, which is highly undesirable. So generally you try to stay away from bolted connections, but if you do use them, you need to make sure that the bolt strength is appropriate. Third point on that list is obviously the hull shape. You'll notice that many mine-protected vehicles have V-shaped hulls, and that is for good reason. Deflection of blast gases is a very efficient method to reduce the load on the hull, and that is something you routinely look to do in your design process. The other thing that you're wanting to try and ensure is that you do not create any gas pockets. And by gas pockets, I mean areas on the hull where gas can collect and not be deflected or escape easily. And what happens in those gas pockets is very high pressures result, which can lead to punch-out failures of the hull. So you typically trying to ensure that gas from the blast can easily be deflected away. The final point in this list is to avoid large changes in stiffness or stress concentrations. Numerous times I've seen vehicle hulls fail due to the fact that they've got very large changes in stiffness in the hull, and at those locations is where the metal will fail. So you're typically trying to ensure that you get gradual transitions in stiffness of the vehicle hull if it's going to be exposed to the type of loadings that you get in a mine blast scenario. Right. The next area where simulation can be a big aid is with regard to human response. This is really the ultimate aim of your vehicle, is to ensure that your occupants not only survive but are not injured. And there are a number of aspects that come into play in this scenario. So first of all, your seat design and occupant constraint mechanism are critical. The seat acts as the primary load path to the occupant, so ensuring that the seat is designed and given the appropriate strength is critical. Second point is the positioning of the seats within the vehicle. There's certain areas of the hull that will deform more than others. So there are going to be areas that are more beneficial to have seats than others, and those need to be identified before the design and the location of the seating is fixed. Another really critical aspect is the way in which the seats are actually attached to the vehicle. You're obviously trying to avoid locations that respond very significantly to the blast loads. So typically you would want to try and attach seats to the side walls rather than the floor of the vehicle, and try and identify locations that respond least aggressively under the blast loading. Another area where people spend a lot of time and money is in attenuation mechanisms to try and reduce the load, the peak loads that are transferred to the occupant under loading. And the final point that I'll make under human response is with regard to floor and footrest design. The peak ankle forces are a critical requirement of certification tests. This is one of the more difficult criteria that vehicle designers find to meet. So you've got to ensure that the ankle forces are kept below a certain value, and obviously the design of the floor and footrest are critical in that respect. Isolation mechanisms are also routinely employed to ensure that these peak forces do not exceed the specified values. Okay, and then the final area where design will aid, where simulation will aid your design, is in the internal layout and packaging. So in any mine-protected vehicle, you'll routinely have a huge amount of equipment and code that needs to be stored and transported, and it's a significant task to ensure that all of this equipment does not act as a projectile when a mine blast strikes. In order to combat that risk, you'll routinely have to design constraint mechanisms and store items in appropriate locations given their threat level as projectiles. One really important point is that because military vehicles will carry ammunition, you need to make sure that any ammunition that can be set off by shock loads is positioned at locations where those will be kept to a minimum. Often you'll have to employ isolation mechanisms there as well. I think the reasons for that are obvious. Okay. Alright, so those are the areas where simulation will aid your design. I'm just going to briefly discuss the approach that you will use typically in performing a simulation. Okay. So we'll use explicit time integration with two spatial discretization methods. Explicit time integration is very well suited to this problem due to the highly dynamic nature of the event as well as its short duration. And then Dytran is very well suited to solving these type of problems on account of the fact that it's got both Lagrangian and Eulerian solvers. So typically you solve your vehicle model using the finite element approach, and the blast will be modeled using the finite volume discretization method. One of the points that I think is prudent to point out with regard to Dytran is its coupling mechanism. It's really robust and easy to set up relative to other codes that I've been exposed to. So basically ensuring that the loads from the blast get transferred to the structure efficiently, and that the structure acts as a boundary to the flow in the Eulerian domain is the task of the coupling, and that is really robust and a unique feature of Dytran in my opinion. Alright, so for pre-processing I typically use Patran, solving Dytran, and then post-processing will be performed with Insight in my case. This is a really powerful tool for visualizing the results. I know there is ParaView available as well, which can do a good job. And that's something that I really recommend if you are going to be performing mine blast analysis. Using a third-party post-processor really does assist things quite significantly. Right. Okay, so next section I'm just going to talk you through a demonstration model that I've created. Basically consists of a World War II era German tank. Okay. The armor specifications down here at the bottom corner give you an idea of the type of plate thicknesses that are involved. So this is a very well protected vehicle, let me put it that way. This model was purely constructed for demonstration purposes. As you can imagine, most of the work that's done in this area is highly confidential, so this model was built purely for demonstration. Okay. This video basically gives you an idea of what's involved in the model setup. We basically have a hybrid 3/50th percentile dummy that is seated within the vehicle. The vehicle suspension is modeled using torsion bars, got its road wheels, along with tracks. Each of the track segments is modeled using individual rigid body with hinge joints between each segment. The hull was obviously modeled using solid elements. I don't know if you could see there, but there was a couple of empty cartridges that are left lying on the floor of the vehicle, which you will see when I show you the results act as very dangerous projectiles. The finite elements that I used here were predominantly hex 8 with a couple of pent elements required where geometry precluded the use of hex elements. That view gives you a pretty good idea of what the mesh looked like. Alright, so just a couple of characteristics. So we've got about 1.3 million finite elements, 1.46 million finite volume elements, and 275 rigid bodies within that model. Okay, so the setup of the mind blast, I've got basically an IED because the charge is significant in this case. Set up under the left track, a 30 kilogram charge. Okay, so I'll quickly show you the results. This video gives you an idea of how the blast gases expand after detonation and their influence on the vehicle within the first 5 milliseconds. Typically, a mine blast transfers the significant portion of its load within the first 5 milliseconds, and then the significant structural response takes place within a tenth of a second or so. This view gives you an idea of the sorry, in a second. Okay, so here you'll see the velocities of the blast gases as they expand. So they reach values in excess of 1,000 meters a second quite easily. Okay, so the structural response, so that initial part of the video showed the mine detonating. So that's the mine going off, and then we transition to the actual structural response, which takes place over a longer period of time. Okay. So from an occupant's perspective, what can be expected if you were sitting inside that vehicle? This view gives you an idea of the type of mayhem that ensues. So the fringe of the vehicle is von Mises stress, ranging from 0 to 600 MPa. Second part of the video shows how those empty cartridges behave when the load from the mine blast is transferred to them. Okay, so one of the areas where you can monitor results very effectively is using time histories. So this image shows with red dots where I've monitored locations that are in close proximity to the occupant. And I've basically plotted the velocity versus time curve there. That's unfiltered velocity. So you could filter that to get rid of unwanted high frequencies, but it just gives you an idea of the information that you can extract. In a similar manner, I've now captured the displacement of those locations over time. Right. Just a different view of what happens during the blast. So you have those shells flying around all over the place, and the occupant obviously gets a very serious load as a result of the seat impact. I mentioned earlier that any loose items within a vehicle can act as projectiles, and those reach significant speeds. As you can see here, I've plotted the velocities of the cartridges over time, and you can see they reach over 15 meters per second, which in a confined space like that can be fatal very easily. So this is one of the responses that I found most interesting. What happens to the barrel under blast loading? The solid piece of steel that deflects very significantly. That I found pretty interesting. Okay, just a plot of the movement of the barrel tip over the duration of the simulation, just to give you an idea of the magnitude of that movement. Right. So that was an overview of the type of results that you can expect from a typical mine blast model. I'll just draw your attention to some useful new Dytran features now. These have been introduced and developed over the last few versions. The first one is 2D to 3D remapping. So typically you would want to try and perform the mine blast analysis using, or at least perform an analysis of the initial stages of the mine blast using a two-dimensional mesh, because you are able to mesh with a lot finer or smaller elements, and that allows you to capture responses that you wouldn't be able to in 3 dimensions. So this image that I've got shown here gives you an idea of the type of resolution that you can get if you do use a 2-dimensional approach. But your approach would typically be to create a 2-dimensional analysis for the initial stages of the mine blast as the gases expand, and just prior to them impacting the vehicle hull, you'll then map those pressures and velocities over to a 3-dimensional mesh and then continue solving the model from there. So that was a really significant improvement that was introduced recently into Dytran. And the second thing is DMP, or distributed memory parallel processing, for the Euler solver. That can give you very significant speed-ups for solving these complex models. Okay, and then finally, I'd just like to draw your attention to a couple of important points that you should consider if you are going to perform mine blast analysis. The first is material models. Material behavior under blast loading is typically strain rate sensitive, so your material models should reflect this. Typically you're looking at Johnson-Cook yield models to try and take those effects into account. The second thing is your mine material model, which typically will be modeled using a JWL equation of state, must represent the actual charge. You need to have obviously a good representation of the energy that is contained within that charge if you hope to get accurate results. The second point on that list is mass, something that is quite easy to overlook. The mass and inertia of your finite element model should reflect that of the real structure. The finite element model will typically be a lot lighter than the real vehicle, simply because you neglect a whole lot of detail and equipment. So that's always one of the aspects that is challenging, is to try and get your model to the correct mass. And then the final 2 points on this list of recommendations go hand in hand, and that is testing and experience. As I've mentioned earlier, you will not escape testing in this scenario. It's necessary to build knowledge and confidence in the simulation models that you build. And also, experience of mine blast tests allows you to have a better idea of what the right answer will look like. I know that sounds really, doesn't sound good, but that is the truth. You need to have some sort of knowledge of what to expect given a certain charge size and vehicle hull shape and plate thicknesses and that sort of thing to verify that simulation models are providing useful results. Okay, so that's the end of my presentation. I've gone through it very quickly. I hope you have enjoyed it, and if there are any questions, then I'd be happy to answer them.